Imagine for a moment you're looking in the mirror in the morning, brushing your teeth, getting ready for another ordinary day. But what if I told you that, according to the fundamental laws of physics, you shouldn't exist? Neither you, nor I, nor Earth, nor the stars, nor the galaxies, absolutely nothing should exist in the universe. The entire cosmos should be just a cold, dark void, without a single particle of matter. And yet, here we are, cosmic explorers, questioning our very existence in a universe that, theoretically, should never have allowed us to exist. Welcome to the Cosmic Frontiers channel. I'm your guide on this journey of discovery through the cosmos. And today we're going to unravel one of the greatest mysteries of modern physics. Why is there more matter than antimatter in the universe? We'll explore the revolutionary experiments happening at CERN, the world's largest particle physics laboratory, where scientists are trying to decipher this enigma. That might explain the very reason for our existence. And get ready, because by the end of this video, you'll discover how a tiny cosmic asymmetry of less than 1/1000% was responsible for everything we see, touch, and are. We're on an incredible journey towards 1,000 cosmic explorers, and every discovery we make together brings us not only closer to that goal, but also to a better understanding of our place in this extraordinary universe. To understand why our existence is a mystery, we first need to learn about one of the most surprising discoveries of 20th century physics, antimatter. Imagine that every particle that forms our body has an identical twin sister, but with a completely opposite personality. That's antimatter. For every electron orbiting in our atoms, there's an anti-electron, also called a positron. For every proton in the atomic nucleus, there's an antiproton. It's as if the universe created a mirror world where everything is exactly the same, but with inverted electrical charges. The British physicist Paul Dirac predicted the existence of antimatter in 1928, when his mathematical equations suggested that every particle should have an oppositely charged partner. It was such a revolutionary prediction that Dirac himself doubted his calculations. But in 1932, Carl Anderson detected the first antiparticle in cosmic rays, confirming that antimatter was not just a mathematical curiosity, but a physical reality. Now here's the problem that haunts us to this day. When matter and antimatter meet, they mutually annihilate in an explosion of pure energy. Following Einstein's famous equation, E equals mc, it's the most efficient conversion of mass into energy we know. If you took just 1 gram of matter and 1 gram of antimatter and allowed them to meet, the explosion would release energy equivalent to 43,000 tons of TNT. It's more powerful than the atomic bombs of Hiroshima and Nagasaki. Think about that for a moment. If at the beginning of the universe there were equal amounts of matter and antimatter, as our theories predict, they should have completely annihilated each other, leaving only radiant energy in an empty cosmos. It's like imagining an epic battle between two perfectly balanced armies, where each soldier has the ability to destroy exactly one enemy soldier. At the end of the battle, no one should be left alive. But here we are, descendants of an army that mysteriously survived. The most precise measurements we have today indicate that for every billion antiparticles that existed in the primordial universe, there was 1,000,000,001 matter particles. This minuscule difference, this asymmetry of just 1 part in a billion, was enough for, after all, the annihilation. Sufficient matter to remain to form stars, planets, galaxies, and eventually, you and I, we are literally made from the remnants of a cosmic war. But how did this asymmetry arise? This is one of the most fundamental questions in modern physics, and to try and answer it, scientists around the world have built the largest and most powerful particle accelerator ever created, the Large Hadron Collider, or LHC, at CERN, on the border between France and Switzerland. CERN is like a cathedral of modern science. Imagine an underground ring 27 kilometers in circumference, colder than outer space, where protons are accelerated to near light speed and collide with an energy equivalent to 2 high-speed trains crashing head-on. In these collisions, for fractions of a second, scientists recreate the conditions that existed in the universe just trillionths of a second after the Big Bang. One of the most fascinating experiments conducted at CERN is LHCb, designed specifically to study the difference between matter and antimatter. Scientists observe particles called B mesons and their antimatter equivalents, looking for slightly different behaviors between them. It's like investigating identical twins in search of small personality differences that might explain why one became more successful than the other. In 2019, the LHCb experiment made a revolutionary discovery. They observed that particles called d-mesons behave slightly differently from their antimatter equivalents. It was the first time this asymmetry had been detected in this type of particle. It's like finding the first clue to a cosmic crime that happened 14 billion years ago. Another crucial experiment is ALPHA, which directly studies antihydrogen atoms. Imagine the delicacy required to capture and study atoms made entirely of antimatter, particles that would instantly annihilate if they touched any common material. Scientists use powerful magnetic fields to suspend these antihydrogen atoms in a vacuum, like cosmic trapeze artists balancing in the air, and then study how they absorb and emit light, comparing them with normal hydrogen atoms. You might be asking, why does this matter? Why spend billions of euros and decades of research to understand something that happened in the first second of the universe's existence? The answer is profound and touching. Because we are trying to understand why we exist. Our current theories suggest three necessary conditions for the asymmetry between matter and antimatter to have developed. First, there must be processes that violate a conservation law called baryon number, allowing matter particles to be created without creating an equal amount of antimatter. Second, there must be a violation of fundamental symmetries, specifically charge and parity symmetry. Third, these processes must have occurred when the universe was out of thermal equilibrium, during a phase of rapid expansion and cooling. This is where the story becomes even more fascinating. The Russian physicist Andrei Sakharov proposed these conditions in 1967, long before we had the technology to test them. He imagined that, in the first moments after the Big Bang, when the universe's temperature was trillions of degrees and exotic particles that no longer exist today were continuously created and destroyed. Small differences in the laws of physics slightly favored the production of matter over antimatter. One of the most promising theories involves hypothetical particles called leptoquarks, which could have existed only under the extreme conditions of the primordial universe. These particles could have decayed in a slightly different way, favoring the creation of matter. It's like imagining that, in the confusion of the first moments of a party, some people chose to use a specific exit that by chance led them to survive, while others did not. Experiments at CERN also investigate the violation of a fundamental symmetry called CP symmetry. This symmetry suggests that the laws of physics should be identical if you simultaneously swap particles for antiparticles and invert all spatial coordinates, as if looking at the universe through a mirror that also swaps matter for antimatter. The discovery that this symmetry is violated in some rare processes was one of the greatest advances in understanding cosmic asymmetry. In 2020, the T2K experiment in Japan made a discovery that thrilled the global scientific community. They observed a significant difference between how neutrinos and antineutrinos change from one type to another during their flight. Neutrinos are ghostly particles that pass through our bodies and the entire Earth undetected. But this discovery suggests they may hold secrets about the fundamental asymmetry of the universe. Imagine you are detectives investigating a crime that happened 14 billion years ago, where the only evidence is microscopic footprints left in particle accelerators. Each experiment is like finding a new clue. Each discovery brings us closer to solving the supreme mystery. Why did the universe choose existence instead of nothingness? Some scientists propose that the answer may lie in extra dimensions of space-time that we cannot perceive directly. Others suggest that dark matter particles, which make up 85% of the universe's matter but remain invisible to us, may have played a crucial role in creating the asymmetry. It's possible that there is a hidden sector of reality, a parallel cosmos of particles that interact very weakly with our common matter, but which was fundamental to our existence. The most impressive thing is that future experiments may give us definitive answers. CERN is planning a successor to the LHC, called the Future Circular Collider, which will be 4 times larger and 10 times more powerful. Space telescopes like the James Webb are observing the universe's first galaxies, looking for evidence of the conditions that allowed matter to form. Gravitational wave detectors may pick up echoes of the processes that created the asymmetry in the first cosmic moments. There is also the fascinating possibility that the answer is connected with other fundamental mysteries of physics. The dark energy that accelerates the universe's expansion, the quantum nature of gravity, the unification of all fundamental forces. All these enigmas may be intertwined with the question of the asymmetry between matter and antimatter. Some theories suggest that our universe may be just one among infinite parallel universes, and that in many of them antimatter prevailed, creating mirror cosmoses made entirely of antimatter. In these universes, there would be conscious beings made of antiparticles, asking the exact same questions as us, but in a reality where our matter would be the exotic one. The search for answers also has extraordinary practical implications. Fully understanding antimatter could revolutionize medicine, allowing more precise cancer therapies using targeted antiparticles. It could transform space exploration, as matter-antimatter annihilation is the most efficient energy source theoretically possible. An antimatter-powered spacecraft could take us to nearby stars in decades, not centuries. But perhaps the most profound implication is philosophical. We are discovering that our existence is not guaranteed by the fundamental laws of nature, but rather the result of an extraordinarily improbable cosmic coincidence. We are the product of an almost imperceptible asymmetry that manifested in the first instance of time, a quantum fluctuation that echoed through billions of years until it resulted in consciousnesses capable of contemplating their own origin. Every atom in our body carries the story of this cosmic victory of matter over antimatter. The carbon that forms our organic molecules, the iron in our blood, the oxygen we breathe, all are survivors of an epic battle fought when the universe was only fractions of a second old. We are literally made of victorious stardust. Experiments at CERN continue every day, 24 hours a day, in a tireless search for answers. Scientists from over 100 countries work together, united by the fundamental curiosity about our existence. Every particle collision is a question directed to the universe. Every detector is an attentive ear, waiting for the cosmic answer. So, cosmic explorers, here are the three most fascinating points from our journey today. First, that our existence is the result of an asymmetry of less than 1/1000% between matter and antimatter in the primordial universe. Second, that scientists at CERN are recreating the conditions of the Big Bang to understand how this asymmetry arose, using experiments that are true works of art of human engineering. And third, that the answer to why we exist may be hidden in extra dimensions, exotic particles, or even in parallel universes that we may never observe directly. This leads us to a profound reflection. If our existence is so improbable, so dependent on almost impossible cosmic coincidences, does that make our life more precious or less significant? I believe it makes every moment, every discovery, every human connection infinitely more valuable. We are the universe becoming aware of itself, questioning its own rules, challenging the limits of knowledge. Cosmic explorers, leave a reflection in the comments. If you could ask the universe directly a question about its origin, what would it be? And what other cosmic mysteries would you like me to explore in our next videos? Perhaps the nature of consciousness, wormholes, and the possibility of time travel, or multiverses and parallel realities. We are on an incredible journey towards 1,000 cosmic explorers, and each of you is fundamental to this mission of making the universe's mysteries accessible and fascinating. If this video expanded your cosmic horizons and sparked your curiosity about our improbable existence, join our crew by clicking subscribe. Like it if you think more people should know about these extraordinary mysteries, and share it with someone who also marvels at the great questions of existence. In the next video, we will explore another enigma that may be connected with matter asymmetry, the mysterious nature of dark energy that is accelerating the universe's expansion. Will the same force that allowed us to exist also determine the ultimate fate of the cosmos? Until the next cosmic frontier, keep looking at the stars and questioning everything.